Since I have some extra time in today's lecture, I wanted to record a supplementary video to emphasize that if you're lucky enough to be solving a matrix equation involving a lower triangular matrix or an upper triangular matrix, matrix equations involving upper and lower triangular matrices are usually pretty simple to solve. For example, let's consider the matrix equation here involving this lower triangular matrix, which I might call L for short. Let me suppose that I'm trying to solve this matrix equation L times Y equals some output vector. Maybe I'll call that B. There is a sense in which a triangular matrix has already been kind of row reduced. If I think about the system of equations corresponding to the matrix equation that's right in front of me, I can almost immediately read this matrix equation and figure out what the solutions look like. For example, this first column would correspond to the first component of my vector y forming the solution. The second column would be y2. The third column would be y3. And so if I read the equation corresponding to this first row, the equation corresponding to this first row would be y1 equals 3. And so that first value of the first entry of the solution, I've gotten immediately from this lower triangular matrix. And the subsequent solutions could be found relatively easily at this point just by using substitution. For example, this second row of the matrix would be 2y1 plus one copy of y2 equals 1 on the right-hand side. And if I sub in my y1 value, I get 6 plus y2 equals 1, which means that y2 equals minus 5. And then I can read the final row of the matrix to get the final equation, 3y1 plus y2 plus y3 equals 5. And again, at this point, I can find y3 pretty easily just by substitution. Plug in y1 equals 3, plug in y2 equals negative 5, and solve for y3, and we get y3 is equal to 1, I think. So because I had a lower triangular matrix on the left-hand side of this matrix equation, I could find the solution very, very easily, almost immediately, by just reading the equations and doing some light substitution. So having a lower triangular matrix in a matrix equation is incredibly convenient. Likewise, having an upper triangular matrix in a matrix equation is incredibly convenient. Let me call this matrix U on the left-hand side. And let me try and find a solution, U times X, that results in this vector Y that we obtained earlier in this process. Once again, because U is already row reduced, if I just read off the equations corresponding to the different rows, and I think about them in terms of what they're saying about the entries x1, x2, x3 of our solution. The bottom row would be saying that x3 is equal to 1. So I've got that value immediately. Then I've got negative x2 plus 3x3 is equal to minus 5. And I can get the value of x2 pretty much right away by just substituting. Plug in x3 equals 1, solve for x2, and I think I get x2 equals 8. And then read the top row, 2x1 plus x2 plus 2x3 must equal 3. If I go ahead and back substitute into that, I get 2x1 plus 8 plus 2 equals 3. So that implies that 2x1 is equal to negative 7, and that implies that x1 is equal to negative 7 over 2. And so with very little work at all, I've gotten the solution x equals negative 7 halves, 8, and 1 to this matrix equation. So I want to point that out, that if you're solving a matrix equation involving a lower triangular matrix or involving an upper triangular matrix, that's a really desirable situation, and it makes solving the equation very, very easy. We're going to be using that principle toward the end of this chapter of the class as we talk about something called the LU factorization of a matrix. So just bear that in mind and hold on to that until we reach the episode on LU factorization.